All right, so yeah, welcome to this talk about creating thousands of databases. It's my first time here in Russia, first time in Moscow. Thank you very much. Ну, я попробую учить русский язык. Да. So it was very nice. My first experience in Moscow was getting a taxi from the airport to the hotel, which cost me like 8,000 ruble, which I then learned is too much. But I'm pretty sure the cab driver needed the money more than I did, so that's fine. Next thing I immediately recognized by walking into several restaurants is they served the best cappuccino I've ever had. So like four different restaurants, and they were all serving top quality cappuccino. So coffee culture here in Moscow is very, 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 very nice. So yeah, let's dive into the topic. So as I said, this talk is about how to operate and create thousands of databases. Few words about myself. I'm the dirty guy on the right side, Julian Fischer, CEO of a company called Any9s. Historically seen, we started as a platform as a service based on Cloud Foundry. So question here to the audience, who knows what Cloud Foundry is and who, yes, you heard of it? All right, that's good. So yeah, we actually started as a platform, but customers around Europe dragged us into consulting gigs a lot because they were building their in-house platforms, IoT platforms, industry platforms, insurance companies, you know, a lot of digital transformation stories to be told here. So life turned us into a consultancy somehow, and today we specialize on operating and automating platforms with a special focus on data services. So the story I'm going to tell is not, I'm not going to show code. So if you want to see code, I'm really sorry. It's more a conceptual talk. It's on how you approach the problem in general. So I leave the choice of technology up to you, although I will give some advice. So first of all, let's look at what is the context of such a talk, because automating data services, well, has already been done several times, but it's always that a context will give you enough to, you know, talk about it, how you can do it, because there are hundreds of thousands of ways on how you could automate it. So first of all, I'm talking about the context that you're going to have a platform. In our case, it was a Cloud Foundry platform, but it could be other platforms, OpenShift or Kubernetes or whatever. But we're looking at the scale of potentially running thousands of applications. So just imagine there's a runtime and there are a lot of applications in there. So depending on what's the purpose of your platform, there may be, that might be an in-house platform of a large corporate customer, or in our case, it's a public offering. And I think the public offering is something we should take in mind when, or have in mind when talking about data service automation, for the reason that in a public platform you have customers, and these customers don't have any trust relation among each other. So this is kind of a litmus test, because you might also be onboarding potential vicious users, especially in a free trial. You often do not have an identity proof, so the platform needs to be more robust, more isolating. Multi-tenancy capabilities need to be more developed than in other environments where you have some kind of trust, where you at least know that your users are, you know, your employees. So another thing is those platforms, they allow you to use arbitrary number of languages and frameworks. So it's a polyglot world. So we use Node.js for this and Rails for that and whatever, Java for this. And also, in contrast to many other DevOps-based operational models where you really have a team that develops and operates software, we are looking at a platform where the DevOps is mainly for automating a process, and it does not It's not the same person who writes the code and runs the code as term of automates the database. But in this case, the database automation is done by one DevOps team, and the application deployment is done against the platform. So the platform is basically allowing users without operational knowledge to operate their applications. Still, they're going to have operational responsibility, just like Werner Vogels from Amazon said, you build it, you run it. So we're looking at an automation where you give the responsibility of operating to someone else without requesting operational knowledge from him. So we are going to look into how this may work. So instant scalability and self-healing is something that we all expect from a cloud-based solution. And just reminding what does a platform from the application perspective does is it allows you to push your app. So in Cloud Foundry it's CF push. For other platforms it might be a different command, but it's pretty much the same thing. And just to get into the idea of platforms, it's worth looking at what happens here. Is in the years before those platform technologies came up, what did we do? We did a lot of chef automation. So we had several different application servers. We had Tomcat for Java. We had Apache for PHP. We had several other WebRig and whatever they are called for Ruby on Rails. There would be like half a dozen for Rails. So the runtime abstracts mainly from the language and the framework you're using. So the concept of build packs was introduced, I think, early 2000, whatever, 7, 8, 9-ish by Heroku. And the idea is that you have code, could be binary code or could be source code, and that you'll have a build pack that is tailored to the code. So it will, for example, turn your Ruby code into an executable command. So in that concept of using a build pack, you have a staging phase where a build pack is being applied, turning your whatever code you have into an executable droplet. That was the language of Cloud Foundry at that time. So if you have a different framework, a different language, it will be a different build pack, but it will just do the same thing. It will turn it into a droplet. So whatever it was before staging, it will be a droplet after staging. So in front of the Cloud Foundry runtime, all droplets are equal. So basically you got something you can start, right? So it's a tar archive, for example, with a command, and you can start it up. So recent versions of Cloud Foundry also allow you to start container images. Could be a Docker image. It's not really a Docker container. It will be started, will be a garden container, but it will take the file system of the Docker container. So you can actually abstract it even further and say, well, something that can be run in a container. Your app is going to be inside. So it's wrapped up in a way that you can just take it from a storage and throw it at some slot to run a container, spin up the container, and off you go. So this abstraction actually creates a lot of potential for further automation. For example, you have functionalities such as assuming this is your runtime and there are two applications. There's one app that's a little, say, has 4 gigs of RAM. The other has 2 gigs of RAM. But there are 2 instances of app number 2 and 1 instance of app number 1. So I want to have an easy command that will allow you to scale up. So I want to have 3 instances of app number 1, and then there you go, you have 3 instances. So you can scale horizontally each application with just a single command. You don't have to, touch any line of code or something to do that. Same for self-healing, because those applications are basically already wrapped up in a way that you just have to start them up. At this phase where staging already has taken place, if one application goes down, you just take the application code from stack and execute it, which happens pretty amazingly fast. So whenever your application goes down, what are the reasons why application goes down? Potentially because of hardware failure, because even with a lot of fancy infrastructure technology, hardware still fails. So at some point, a server goes down, the platform will recognize that and restart it somewhere else. So those are the things that I would expect from a modern platform, which is kind of a paradise for applications. But what is the paradise for backing services? So this is a question. If you look at such a platform, which may be able to serve thousands of applications, what do you do with stateful applications? Because this only works if your application does not have state. So this has been described in the 12-factor manifest, also written by Heroku back in the days. And it's just assuming that there's somebody somewhere who will give you a backing service and will maintain state for you. In the business model of Heroku, this meant there were third-party add-on providers who will do that for you. If you are building your in-house platform, you have to solve that riddle yourself. So this is basically what this talk is about. As the time is limited, we are going to have a conceptual view over this. So the missing is a solution to serve thousands of data services. And I use the term data services similar to backing services. It could be a database, it could be a message queue, it could be a search server, it could be a cache. So basically everything. So what we'd like to have is our runtime on the left side, and well integrated on the right side, a solution that serves us data services in the same scalable, self-healing manner. So putting that into a mission statement is we would like to providing a growing number of data services with a full lifecycle automation of thousands of data service instances across a wide range of infrastructures. Wow, that's a long sentence, so let's disassemble it. So a growing number of data service means that we really want to have a lot of them, because if you go down the road of having microservice-based architectures, this one microservice is going to be storing information in a document. Another would be storing information in a relational database, because whatever you need transactions, for example, and because all those bits and pieces need to asynchronously communicate, you want to have a RabbitMQ. So I'm saying is that there's more than just a SQL database today, and the NoSQL world is adding more databases constantly. So if you look into the topic of automating data service in general, you're not looking at a particular data service and how to automate it. You're looking at a bunch and a growing number of data services. Now, automation means that you, from the creation to the scaling to the update, you really take care of the life cycle of such a data service. It's a lot of people when they talk about DevOps, they look at a cold deployment. But it's not the cold deployment that really is the problem. It's the problem of what you do with your database after that, because the database has state. So if you do an update, or you need to update your operating system, this is potentially creating conflicts. So you have to take care of the entire life cycle of such a data service, and data services tend to live very long. And also we need to create thousands of them. As we said, it's going to be a large number of them. And they can be of different sizes. They can be small, they can be large, they can be clustered, they can be solos with just a single virtual machine. And we want to provide them across a wide range of infrastructures. So why is that? We started on vSphere, with Cloud Foundry was at that time well developed against vSphere, but it was a kind of costly thing, so we decided to go and migrate to our OpenStack, which we at that time operated in a data center close by to our company, which was the worst idea I've ever had, because OpenStack is a piece of beep. Yes, I didn't say that. So we went through the valley of darkness with OpenStack, and now our production systems are running on Amazon, and our staging systems are running on vSphere. And we migrated our platform, including hundreds of running apps, with less than 30 minutes downtime just to give you a feeling of what is capable, what is possible if you automate in a way that it is infrastructure independent. It's possible. So we would like to serve both public and on-premise clouds. So you're looking at Amazon, Azure, and Google Cloud Platform for public instances. Our international customers, for example, they often start with two different types. Ones that are on-premise customers, they will start on-premise, and they will see that they will run into infrastructure issues because vSphere is, well, it's something you really have to put effort in. Where Amazon is something that you can, it just works. It works to a solid degree. It gives you, it will also, there are going to be issues with Amazon too, but it's in a way that your software layer, if well automated, can cope with it. If your customer goes into the Asian markets, then you're going to look at Azure, because Azure and Microsoft has very good contracts with the Asian government, and what they do is they do really run these infrastructures under the local jurisdiction. So in Germany, for example, there's an Azure being operated by Telekom. So you don't have the problem that the parent company of your infrastructure provider is potentially subject to the US Patriot Act, which breaks everything that data privacy, should ensure you, including the safe harbor, which is a kind of ridiculous self-certification, so you can throw it away anyway. All right, and of course, OpenStack and vSphere for on-premise scenarios. Last but not least, we would like to integrate with those platforms who currently exist. So open source Cloud Foundry, Pivotal Cloud Foundry, OpenShift, and Kubernetes are the obvious ones. But maybe there are more to come too. So when looking into the automation of data service in general, there's a set of requirements you always want to have your eye on. I won't go into the very details of each, because you can basically give a 45 minutes talk about each of those aspects. So let's just see that there's a number of them. So portability, for example, would mean to create or be able to operate on several infrastructures or several and integrate with several platforms. So on-demand self-service is one of the most important cloud requirements. It means that the platform user can, for example, create a database without, calling someone. So it's just one command and you have your database ready to be used. One command and you deploy your app. So let's look at those we'll repeatedly hit in this talk. It's portability. Multiple infrastructures, multiple platform compatibility. It's scalability. Scalability means I want to create thousands of databases, but I want to scale a database that's already there. So I want to create a small database and turn it into a large database, because that is something I would like to be doing, especially because there's data involved. And if a database, is more frequently accessed, you also want to take care of vertical scale-outs. Last but not least, production, no, it's not last, but it's important, production readiness. So we've seen solutions that, for example, are based on shared clusters, where you have a shared database cluster, let's say a Postgres, 3 virtual machines, and then you carve up this cluster into several databases and serve them to the customer as the database. While this is easy to be done, it doesn't scale very well, because for 2 reasons. The first reason is you never know what somebody does with a database, and the means of isolating customers within the database is usually not strong enough to really ensure that one customer cannot affect the other. So it's a weak isolation, and for that particular reason, a bad idea. And the second thing is, especially due to the weak isolation, you never know when a database is really full, because it also depends on the usage. So you don't have this high tide threshold where you can say, well, now my database is full. If you even solve that problem, you would run into a fragmentation problem, because then you have a database with 10 customers, 5 go away. So you have to have more of these clusters, and you have to balance incoming new database requests to those different databases. At some point there might be even, well, let's say only 10% databases on a server, so you have to consolidate them. So this is going to be very, very complicated very fast. So we're looking into a paradigm that gets around that, and obviously, again, customers should be able to do everything themselves. So how would you build something like that? First of all, we have to look into the different categories of things we have to do. So because we want to have a on-demand self-service, we would like to provide an API. Because with an API, you can basically automate it. Like you have a command line tool, or you have a web UI, everything in the end talks to this API. So we need an API. We need something that takes care of the heavy lifting of the automation, because I don't want to create virtual machines myself. And as data services, they have very different operational models. It's very likely that you'll have to automate each data service itself. So you have to provide data service specific automation. So those are the three categories. Now, Cloud Foundry, they came up with a contract between applications and data services. It's basically already in the, well, let's say, mental heritage from Heroku, that you have an app that binds to a data service, and this binding represents access credential. So that is a basic concept that existed for years, and it's been proven to be very, very solid. And over the time, they took that contract that was built into Cloud Foundry as an API description. So if you want to integrate something to the Cloud Foundry marketplace, it needs to implement a certain API standard. And this API standard now has become a Cloud Foundry independent standard, so it's worth looking at it. So the Open Service Broker API is a new industry standard for data service provisioning. So currently committed people or organizations such as Google, Pivotal, IBM, Red Hat, Fujitsu, and SAP. And most interestingly, you will also see that multiple platforms are already supported. So the newer versions of OpenShift are going to support it. Kubernetes is going to support it at some point. So it's definitely, if you want to create an API to create data services, the Open Service Broker API currently is possibly the best thing you can choose. Just to give you an example of what it does, it's only, well, there are several endpoints you have to implement. Not all of them you really have to implement. Some of them are mandatory, some of them are optional. But assuming you want to provision a database, what do you need to provide? So the first one is a catalog information, which is just telling the Cloud Foundry marketplace, I'm a service broker for MySQL, a relational database, and I offer the following plan. So it's basically, it's the offering, right? The product page, a metadata for product page. And then there is a method for creating service instances, which means provision a database for me and create a binding. And a binding means that an application requests access to a database. So you as the developer will push an app, will create a data service, and then bind the app to the data service, which means that a database user is created, and this app will have access to that user credentials. So each binding is a unique set of access credentials that is only known to that particular app accessing that particular data service. So in the end, that's what I just explained. We just filled the first box because we know what API to implement. So the Open Service Broker API does not define what the service instance actually is. So you can say, well, it is a database in a database server, or you can say it's a database server. As I explained earlier, any approach that's based on shared clusters is likely to give you a lot of headaches. So it's not recommendable to do that. From my perspective, the architectural pattern that works in the biggest scope possible is the on-demand provisioning of dedicated data services, which means that at a point of time when the customer performs, in Cloud Foundry terms, a CF create service, you will provision a virtual machine as the data service instance. So your customers want to have a MySQL or Postgres. They will, well, in this case it's a MongoDB, they will just perform this command and they will have a dedicated virtual machine equipped with Postgres or MongoDB in this case, ready to be used. So that could be virtual machines of different sizes, and they can be different service plans. They can be structurally different. So for example, this command will lead to a cluster comprised of 3 virtual machines, which will represent a data service instance that will you can bind that to your application. So on-demand dedicated means that you, whenever the customer demands it, create or destroy virtual machines, and those virtual machines will automate the entire life cycle of the particular data service instance. So obviously there are some technical challenges. Most importantly, there is state. And as state is handled differently in every backing service, the operational model of that backing service will be very different. So for example, if you look into Postgres, you have asynchronous replication, but no cluster manager, no failure detection. So you have to add a component who does that for you, for example, the replication manager. MongoDB, for example, has also asynchronous replication, but inherently is capable of performing the failover, right? So they will be different. So the data service automation will be different. But and this is one of the most important concepts to understand here, if you want to automate the creation of virtual machines for the purpose of storing state, you have to think about where to store it. So in an application scenario, you just fire and forget. Your application will be launched, it will be recreated, and because there's no state, there is no data loss. But for data service, we have state. So where are we going to store it in a way that we can still perform the same self-healing? And the answer to this is also pretty old, because everybody who has ever used Amazon possibly has seen that you take a virtual machine and you attach a persistent disk and you store your data on that persistent disk, which is possible because nowadays we have 10 gigabit Ethernet, which is a low latency, high bandwidth connection within the data center, connecting a remote storage server to your infrastructure host where your virtual machine is. So store your data at a remotely attached plug device at persistent disk. Basically looks like this. You create a virtual machine and then you attach your disk, and that is where the data of your database is. Nothing else, right? So the database process itself and all the libraries you need is on the ephemeral disk, the disk that's attached to the virtual machine. Only the data is separated. Now, the persistent disk has a file system, so it's not solving all the problems, but still you need replication and backups. If something goes wrong, you still be able to recover it. However, what it gives you is a separation of life cycle between the virtual machine's life cycle and the data's life cycle. And that's the biggest advantage we can get. And it's worth the potential loss of performance because we have a remotely attached storage device. And we solved the problem of storing state. So now let's look into, I will come back to that storage thing later. So now let's look into what actually needs to be automated. So looking at a data service instance, a database for example, you have a hell lot of things to take care of. You need to provision the database server, which means a virtual machine, install the software, configure the software, then you have to organize apps may consume it, debug, update the data service version, update the operating system, backup data, scale out the virtual machines and or the service, which may require reconfiguration, as well as destroy the whole thing in the end. The question is, can you do that 1,000 times with whatever you're doing now? So at the point we started to dig into that, we've been using Chef, and the answer to this was no. We cannot do that 1,000 times or 10,000 times. So we had to change the way we do it. So one of our strictest rule is you either automate it or you delegate it to the application developer. So either it's so simple that an average developer can, self-service it, or it needs to be automated. There's nothing more in between. And this is a lot of scope where DevOps are at home, especially if they use Ansible and Salt and Chef and Puppet. They are the glue code in between. But with that approach, you take away the glue code and you automate it, or you make it a decision that the app developer can do it. This obviously leads to a big challenge in automation. And while there are so many different automation technologies, and I'm not a technology evangelist, I would like to talk about Bosch, because it is Bosch that lets you handle and orchestrate the life cycle of distributed deployments at large scale against infrastructure and gracefully deal with that problem of state. So designed as to run Cloud Foundry, Bosch is one of the most underestimated automation technologies out there at the moment. So you can basically tell Bosch to talk to your infrastructure API. It abstracts from it because it has a plug-in system so that you can, talk to several different infrastructures. And really, your Bosch releases do not depend on the infrastructure. So it's with Chef. You can use Chef to automate against multiple operating systems, but you have an if-else condition then in your cookbooks, which is not the case in Chef in Bosch. So you tell them to create a virtual machine, and it will also take care of attaching this creating and attaching this persistent disk. So what I'm saying is that this particular design pattern is very good for orchestrating the deployment of large distributed systems, stateful distributed systems. So for example, if you deploy Cloud Foundry with Bosch, then you'll deploy several of them. So you have a blueprint that describes a distributed system as complex as this. Cloud Foundry currently has, I think, around 50 moving parts, different microservices that need to be deployed, and it can all be done with Bosch. So if it's good enough to deploy Cloud Foundry, why shouldn't it be good enough to deploy our data services? A few words about Bosch and its terminology. It's what a cookbook is in Chef. It is a Bosch release in Bosch. A Bosch deployment is something you actually execute. So you upload a release, which is an abstract blueprint of your automation, but it is the deployment that is something you execute, because you have to fill in some blanks. A deployment also depends on the stem cell, which is basically just an infrastructure-specific disk image. So it's a Ubuntu for AWS. So Bosch has stem cells for different operating systems and different infrastructures ready to be used. A deployment contains a release, the abstract automation, and a manifest, which fills in the blanks. For example, how many cloud controllers do you want? How big of the virtual machine size do you want to assign this component to? But you also describe processes you want to start up. So for example, in the case of a database, you not only describe the virtual machine you would like to have, the size of the disk, the software packages you want to install, but also the processes you want to have started, and it will also take care that it remains started. So Bosch deployment manifest is where actually the deployment is then assembled, and your infrastructure specific settings are in a cloud config. So you can basically have an abstract automation, that's your release, a manifest that describes the deployment, and then the configuration of AWS versus Azure versus OpenStack. So as you can already, derive from that description, this perfectly fits into our requirements. So with Bosch, you're infrastructure independent, and you automate once and deploy everywhere. So basically, whenever you have automated, you just point to a Bosch that's on a VMware. You create your distributed system there, and you can use the same automation and deploy to AWS. And we're talking about real reusability, not this kind of if-else support, but real reusability. So yeah, switch deployments between clouds would be keeping the same release, using a same stem cell specific to the new cloud, adapt the cloud config, and that's it. Just to give you an idea on how easy it is. You're also being operating system independent because you're compiling software from source. So it doesn't use distribution specific packaging systems or directory structures. It uses its own structure, which is kind of cumbersome in the beginning, but once you have what you need, it's awesome because the reusability of your automation is endless. So a Bosch release does not depend on the operating system. The operating system dependency is kept in a stem cell, which is basically just an operating system image with a Bosch agent, the actor on a virtual machine. So yeah, I have to skip a few slides because I have plenty of them. One thing is very important is once you've deployed something, it is scalable. For example, a database. You described it once, you can perform that deployment 100 times. So you can deploy your Postgres, for example, 100 times. Scaling out a Bosch system is therefore easy. You keep the same release, you use the same stem cell, you change the manifest, you push a button, you're done. Now we come to something that directly comes from the storage concept I earlier introduced, which means vertical scale out of databases or anything you deploy with Bosch. You basically get this for free. So let's say you have your Postgres database and disk is about to become full and the CPU is heavily utilized. What you do is with just a single configuration, line of code in a configuration file, not in an automation file, configuration file, you push a button, and what Bosch will do is take your database, it will unmount the persistent disk, destroy the database, it will recreate a database twice the size, create a persistent disk twice the size, copy the data, destroy the old disk, and you vertically scale your database. Now we do that with 3 nodes in a Postgres cluster, so you're triggering failovers 3 times. Then you have a vertical scale out of your database cluster without a downtime. And now you get that nearly for free, just by using that paradigm and that automation technology. Bosch deployments are predictable, which is one of the most important things when deploying at scale, is because source code is compiled in freshly created VMs. Whenever you do significant changes to the system, VMs will be recreated from scratch. So it's not converging like creating small steps and you do that throughout the life cycle. This won't work because updating and so on, there can be mistakes, there can be errors in automation. How would you ever recover from a failed run of a chef cookbook without intervening manually? So in this case, you just create or fix the automation and you just recreate the virtual machine from scratch, reattaching the data. So in order to protect your data, you have to create backups of your data, fair enough. But because it's highly automated, including the orchestration of virtual machines, it's just a few commands to create, for example, 1,000 databases. And because it's always the same procedure, it's very reliable. There are no leftovers of prior runs because always new VMs are used. This makes it also very repeatable. So executing a specific Bosch deployment always leads to exact the same deployment. Even, and we just recently took our continuous integration pipeline, which we use to deploy our data services, and we took it from Amazon to Microsoft Azure without any modification. It just works. Now you deployed something with Bosch. Postgres, for example, you'll get self-healing from process failures in a way that your Postgres, for example, just the process dies. Process monitor is already configured for you, will be restarting your Postgres service. So now, if the process monitor fails, which was monitored in the past, then the Bosch agent will recognize it and restart Monit for you. So your monitoring system is also self-healing. But more importantly, if a virtual machine fails, for example, if an underlying infrastructure host goes down, Bosch will recognize it and Bosch will recreate it, because the data is not affected, because the data resides on your infrastructure. So let's sum up. With Bosch, With Bosch, you have also filled the plank of the last of the automation middleware. So all the rest you have to do is you have to tie it together. So this is what we've been doing. We created a service broker, a component that creates Bosch deployments for you, and then subsequently talks to a Bosch. So with this architecture, then you only have to create new Bosch releases to add more data services. So the architecture looks in the end. This is how our requirements map to the particular features. Portability has been supported by Bosch, and regarding infrastructure independence, and by using the Open Service Broker API, we have multi-platform support. The on-demand dedicated approach is only possible because of Bosch, and you can also see that it is the reason why so many of these requirements are fulfilled. As I stand here, we've done that with those 6 services. There are a lot of components we share in common. So I can say, well, it is reducing the amount of adding automation for a new data service to roughly 4 to 6 weeks for a production version to have. This is what we wanted to achieve. So a few words about finishing up would be, how would you then operate them, thousands of those instances at a scale? You definitely need a CI pipeline. So in our case, we monitor upstream data service versions such as Postgres. We automatically trigger the creation of new releases. We'll have excessive test suites that will go through the life cycle of a cluster, test whether everything works. And then we create our any-nines releases, which we will then use another pipeline to ship it into multiple customer environments, who will then use subsequent automation to recreate all the service instances. But the whole value chain is entirely automated. So you can do that at an arbitrary scale. So yes, I will go through that a bit and go to the ultimate question, which would be, can you handle more than 1001 data service instances? And yes, it is absolutely possible. What I can say is that creating 1,000 virtual machines with that solution isn't hitting any bottleneck at all, because you rarely create 1,000 virtual machines at the same time. It's usually done over time, though. There's a little bit of deletion going on, there's a little bit of creation going on, so it's a fair amount of things. So 1,000 is not something we really fear. So we are looking into large accounts where a large number of developers are going to use. So the more interesting question is, can we also serve high frequented platforms? And we do perf tests around this. For example, this is just an excerpt from it. You can create 750 databases in just 53 minutes, which creates a virtual machine. This is on Amazon in 7 minutes. If you do that on your vSphere, this might look different because vSphere is not very scalable. But you see that the queuing time in Bosch, the amount of time required to perform a Bosch task is crucial. So obviously, scaling Bosch is key to that solution. Summing up, Lifecycle Automation is feasible. Open Service Broker API is a new standard. Choosing the right automation technology is key, and don't do it without continuous integration and continuous deployment. And now I'm open for questions.
Can you compare Bosch and Terraform? What's the difference?
We actually use Terraform in some environments to prepare the deployments of Bosch, because Terraform is very comprehensive in terms of, for example, creating security groups on vSphere and networks and so on. Those are the things you usually do manually or script otherwise with Bosch. Then you deploy your Bosch, and then Bosch takes over. What we found out, so we use Terraform to prepare Bosch deployments, but we fail at that because Terraform is pretty weak, for example, on vSphere. So it does still lack the implementation of some of the adapters we need to really use it. But I'm not an expert in Terraform, so I have engineers to do that, so I cannot go into more depth of that answer. Right? Yeah.
If you host a company that offers cloud data solutions for clients, my question is, how do you assure your clients that their data are not shared between other clients? Maybe you encrypt databases?
Most of these environments are dedicated, so that one client has its own data center or his own Amazon account. So we deploy that solution into his account, and then he uses that automation to deploy database for himself. So he will own the data, he will own the infrastructure account. We only deliver the automation. So the CI pipeline you have seen in that earlier slide, this one, you see platform 1, platform 2, platform 3. Those would be customer deployments. So the customer has a CI pipeline that will pull new releases from a S3 bucket, for example, and then deploy it to his platform. So he will own this. It's not a software as a service solution only. We do that on our platform, but it's actually a thing you can take on premise. All right? Yes?
Yeah, interesting question. How about distributed file systems? Do you use it? Has it any way to implement working with Ceph, cluster, or better in cloud using local file system attached from provider?
Well, we do. The state is stored into a block storage device. So you'll have a file system on top of that. That is Bosch managed. We don't touch that anywhere else. Does that answer your question? Or do you mean how do you cluster service instances?
Yeah.
So for example, Postgres or Mongo, all the services we automated, they come as solo as well as clusters. The automation can do both. You just choose in your when you create a database, which one do you want to have? So you spin up 3 virtual machines, and the automation will take care that these 3 virtual machines will be able to talk to another. So we use a highly available DNS system that they can also use for service discovery. Console.
Okay.
Yes?
I got a question regarding the self-healing. How do you manage the issues with, for instance, flood states, which actually led to the service failure, for instance? Then you try to self-heal the VM, it loads that flood state and it fails immediately. Or some issues with VM failures, which led to a persistent disk data inconsistency. So that you just cannot restore your service.
Yes, that's an interesting question. So clusters fail from time to time, and even the infrastructure providers may fail from time to time. That's why we have an integrated backup and restore framework. So the customer can create backups before performing a potentially dangerous operation, so that in the worst case, you just throw away everything you've deployed and recreate it from backup, which means just spin up a new database and load the backup, right? So this is the worst case. And it's very important because if you really want to go down full lifecycle automation, this is a case you have to be prepared for.
Okay, and which component performs this backup?
it's a component we've developed. So there's which each virtual machine we ship, there's a backup agent shipped with it, and you can trigger that backup agent through a UI or an API as a customer.
Okay, thanks.
You're welcome.
Thank you very much. Unfortunately, it was the last question. We are out of time. Thank you very much for coming.
Thank you very much.